We're now in this section 4 of Laplace transform. This is page 34 of the slide. Why Laplace transform? The motivations. Well, maybe the first thing to tell you is that this is the most important property that we are exploiting in Laplace transform. The convolution in time is a very expensive business when we perform convolution in time. In the frequency domain, like Fourier domain, we have seen that it is multiplication in the S domain. Similarly, for when we transform a signal from time to the S domain, the Laplace domain, convolution also becomes multiplication. So this interesting and important property remains. There are many other useful properties. Some of them are the time shifting property, frequency shifting, initial and final value theorem, which we will exploit in this course. What else can we use Laplace transform for? Well, we can easily study whether a system of an LTI system is stable or not stable when we generate its Laplace transform. We can study the pole positions of HS and very quickly we'll be able to determine whether the system is stable or not. We also can find the impulse response simply by performing the inverse Laplace transform of the transfer function h of s. Now, Laplace transform is also widely used to convert differential equations into algebraic ones, and we solve for that very quickly. Secondly, Laplace transform exists from a wide range of signal f of t. We can convert f of t into f of s and convert f of s back again. So this is the existence and the uniqueness property. It can be applied for a wide range of signals and functions, and therefore this is one of the main reasons why Laplace transform is so useful. Let's have this example. Why transform? Why do we not deal with the signal directly, like in convolution? Why do we want to change something into some other representation? The easiest example I can give you is this expression, y equals to a times b divided by c. Now imagine if a and b are very big numbers as well as c, and that multiplication, you know, is an expensive business, and division is as well. What can we do? When we transform y into the log domain, the multiplication becomes addition and division becomes subtraction. And this expression done in log domain is simply log a plus log b for the multiplication of a times b minus log c for the division. Although our answer is still in the log scale, very quickly we can find the inverse of the log to get y just by doing this. So in this example, we know that it is more economical and it is more advantageous to us by using the log to do multiplication and division, especially when we are doing millions of them, for example. So the other interesting thing, of course, is that if you have infinite precision, no information is lost. Okay? Right, of course, there's some constraint. In the log case, you cannot divide by a negative log number and so on, or multiply by a negative log number. Right, what about the Laplace? So I'll give you this example. I've told you that when we have signal x of t, and we have an LTI system, and we have h of t, the impulse response, the output y of t is described by this convolution equation. X of t convolved with h of t, and this is the convolution equation. Now, convolution is very expensive because to just get a single element x of t, you have to perform this convolution. And if h of t is very long, then this integration is an expensive business. So instead, what we do is that we perform Laplace transform. We get x of t into x of s, h of t into h of s. H of t is the impulse response, h of s is a transfer function. Y of s, which is the Laplace transform of y of t, is simply x of s multiplied by h of s. The convolution property in time becomes multiplication in the s domain. Then, lastly, to get y of t is that we perform inverse Laplace transform of y of s. That's all. And of course, we know that this is the equation to perform inverse Laplace transform, but we don't want to deal with a complex integration. So what we do is that we do the engineering approach. We perform partial fraction expansion using y of s. Then we typically will get it into this form. Some factors with some partial fractions, and then each one of them can be looked up from a table, and then we get y of t. So this is what we do. So this picture shows you why we perform Laplace transform when we want to deal with LTI system to compute the output. What other things can we do? Well, we can do things like this. Final value theorem. What is final value theorem? Let's see that we have this problem we want to solve. We want to find y of t, and we want t to goes to infinity, and we want to find this final value. Now, if we have already f of s, what we simply need to do is to multiply f of s by s and let s tend to 0. The value computed in this expression on the right hand side is y of t as t goes to infinity. Now this is a much cheaper way. Imagine if you have to compute y of t recursively, and it's very expensive. Okay, so this final value. What are the things we can do? Okay, well, we told you that if you have h of t and you perform Laplace transform to get h of s, immediately you can see whether the system is stable or not, simply by examining the pole position. So what you do is that you have h of s, and this is the real part of s, and this is the imaginary part of s, and this is the s-plane. And if you have pole sitting here, for example, then this is stable because the pole is on the left hand side of the s-plane. So what we do is that we draw where the pole is, and everything on the right hand side is the ROC, because this is for a causal LTI system. So as long as the pole is on the left hand side of the imaginary line, and the region of convergence, or I should say all the poles and the region of convergence covers the imaginary line, then it is stable. We'll give you the details why later on. And lastly, we show you the last example why we're interested in Laplace transform. We can convert a differential equation into the algebraic form. This looks like a differential equation. Y double prime is d2y dx squared. Y prime is dy dx. So we have the second order differential equation, and then we have some initial value. Y of 0 is 1, and y prime of 0 is equals to 0. Right, when we have this equation, what you do realize is that what we can do is that we take this expression y double prime, and the Laplace transform of this is this expression here. We have converted a differential equation into an algebraic form. S squared is a variable s, while ys is the y that we're interested in. What you realize is that once we have converted into this form, for example, y prime will be converted into this form, and then the last one, 2y, is converted into this form. We have converted a differential equation here into an algebraic equation, and very quickly we can find what is ys. equals to some expression over here, and then later on simply we can perform inverse Laplace transform to get y of t. That's the idea. Okay, so take a look at this page, and this page basically summarizes why we perform Laplace transform using these few examples over here. Next page, I will give you another picture of this example, converting differential equations to algebraic form. I took these nice pictures from a website, and what does this show? On the left, we begin with differential equation. We perform Laplace transform and we get algebraic equations because what we have is ys multiplied by some function. And then when we solve for this, what we are doing is that we want to have ys equals to some expression plus some expression where these expressions are in the lookup table. For example, 1 over s plus 1, 1 over s, or 2 over s, and so on and so forth. And once we have that, we can simply perform the inverse Laplace transform to get y of t. So this is their example they have given us. Sometimes these are called initial value problem because the initial values of y of 0 and the preconditions are there. Over here, it shows the Laplace transform as a machine that eats up differential equations. These are differential equations. And then spit out y of s, some algebraic equations. And then when we manipulate, we are manipulating it as in, they are just algebra. We are solving it algebraically. Ys equals to something. Once we have in this form, like I said, these are individual forms that have lookup tables. And we again use a lookup table to perform the inverse Laplace transform. We never, in our course, we'll never use complex analysis to perform the inverse Laplace transform. We'll simply use the lookup table. And this is a solution. So again, this is a very nice picture of the overview of how we are using Laplace transform to solve differential equation.